Like I think some of the students are asking me in email, but I don't think the students are here now. So maybe I'm just waiting for him. Because especially in the chapter 11, um, in the chapter 11, there is some how to say that a lot of definition and theorem, and most of the theorem, if you don't read carefully, you will doing the theorem or use the theorem in a wrong way. So you need to carefully read the theorem, and that's the suggestion that I can give to you. Now we already finished all of this, right? So um, from here, uh, the point is, if first, if you have any functions that you can make representations in sums in the series, you can do that. By doing so, you are approaching the geometric series, right? And you are changing or replacing the x with this part, and you need to multiply with this constant, right? Like this one, okay? Or if you have the similar form, but you know this form is the derivative of the first function. So you may derive this, and you need to also derive the sum for the series. Okay, so that's how we can see all of this connecting. Okay, and then what's the importance of these functions and the series? Okay, the important is, if you have any functions, and then you can simulate the functions into some forms of formula, and then you want to know some specific value at certain points, you can then you can approximate with the series, okay? Because you can add the series to the infinite amount. Because if you have like any calculation that it suggests that okay, it's infinite amount, but you are not really sure how much or the specific value that you are going to be calculated, right? But if you are knowing that, okay, I can also read that as a function, then you can draw graphs, right? And it can help you understand better. Okay, so it works reversibly. You can see the functions, and then you can see the function itself as a sum, or you can see the sum as a function. Okay, that's the important thing about this part. Okay? Because this is, I think, in most of the cases in the future, like when you are dealing with some algorithm, some data set, you will have these connections. Okay, and maybe the formula itself is not as simple as this is. Okay, maybe it will be more complicated, but you need to at least having observations that the functions can represent the sum, or sum can represent the functions. Okay, okay, that's the deal, and you can do the derivative and do the integration, and all of this part is also affected by the derivative and integral. Okay, now we are still dealing with the representation, but in a different way. It's called the Taylor and Maclaurin series. It seems a little bit complicated, but actually, it's if you see or you understand the pattern, it's not that difficult. Okay. So let me write here. Wait. Let me write Taylor and Maclaurin. Taylor and Maclaurin Series. Okay, actually, both are similar, just a few differences. So if you remember at least the Taylor, you will also remember the Mclaren. So just make sure you understand the Taylor. Okay, the Taylor. Okay, the first thing is, let me write. Uh, Let me write the functions similar with what we have right before. We have C and then C2, and then the x variables will be having a squared. So the same for the cube, and it will have until some n. And the convergence should be applied here, right? Okay, so to be converges, the x minus a should be less than r. Okay, notice these functions. If we put some value, let's say x is equal a, then all the x minus a will be removed. We can remove that. Okay, so and we can write that fa is equal c0. Okay, let's write that term. Okay. 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 Now the second, let's write the derivative form. Okay, then we can write c1 and then plus 2c2 and then plus 3c3 x minus a squared. Or let me continue to 4. 4c4 x minus a cubed. Okay. Now the second one, we have the derivative form. And similarly, if we can imagine the x, so if x is equal a, this will be 2c2. C1, sorry. Okay. And let's do the same thing. So derive. So what we are going to do here, okay, from the first fx, we are going to derive until maybe 5 terms, and we will conclude from the patterns that we have. Okay, so that's the first thing. So the second derivative, it will be 2c2 plus. Now let me write this as 2 and then 3, c3 x minus a. Okay, and then plus, we derive another one, 3, 4, c4 x minus a squared. This is all should be the same here. Okay. That's the third one. Same thing, we are equaling x to a, so that the second derivative with a as a value will be 2c2. Okay. Well, let's do it. I will have this as the last one, the fourth derivative, or the third derivative, f. So this will be 2, 3, c3, and then plus 2, 3, 4. Okay, c4, and then plus, maybe the other one will be 3, 4, 5. And then same thing, equaling x to a, and then we get f. This will be 2, 3, c3. Okay, now look at what forms we get. Okay, from the first derivative we have 2, 3, 4, and that's the result of derivative, right? And if we derive this 3, it's 2, and multiply by 3. So it should be 6, right? But I want to write as 2 multiplied by 3. Okay, and then 3 multiplied by 4. And if you look at this 2, you derive 1 here, 2, 3, 4. It becomes 2, 3, 4, right? Same thing happened here, the cube one. So 3, and then 3, 4, 5. Okay, so we can write this 2, 3, 4, 3, 4, 5 as the terms in the factorial. Okay, now let me write this as 3 factorial c3. Okay, so observe the pattern. And then we arrive at the conclusion that if we differentiate for some n, okay, for some n terms, okay, of a, we will get 2, 3, 4, and then until n, and then cn. Okay, or we can write n factorial cn. Okay, and solving for cn, we can write cn is equal fn a divided maybe. And the formula is still valid if we use the n equals 0, because 0 factorial is 1, right? So it's still okay if you start from n equals 0. So now, if you have the power series, okay, the power series representation, you can write down, or you can find its coefficient with these forms. Okay, we haven't go for the Taylor series yet, but this is the introductions for the Taylor series. This form, actually, the Taylor series. Okay, now let's write here some theorem. So if a function has a power series representation, let's say at some value a, okay, and if the functions is, let me write the general terms. Okay, if this is the definitions, then its coefficient. This is just what we have done before, but I'm writing the official definition. Coefficients given by Cn okay. And now, using this formula, put into the series So what we are going to do is see this form. It's Cn, right? Let's substitute this Cn into the general term. And after we substitute, we expand the form from this. Okay, so we expand the series. That's the Taylor series. Okay, that's the Taylor series. Now we have the fx. Let me write the Cn. And then x minus a with the power of n. If we expand from 0 and then 1, 2, 3, let's try some n terms. We will have the first one will be just a, and then plus, and then let me write this as 1 factorial x minus a, and then plus f, the second derivative, divide by 2 factorial, and then x minus a squared. Let me put this. And then plus the third derivative, if you want to write with 3 or 2, I think that's fine. Because if you see 4 or 5, if you write this with, maybe it's too long. So you can write 2 or 3, that's fine. And then x minus a cubed. And it's still plus some terms until n, right? So this becomes, this whole thing is what we call as the Taylor series. Okay. So this means if you have any functions, okay, that you can think some derivative of that function, you can derive maybe 2 times, 3 times, 4 times, and you can maybe derive until some infinite value, right? Then you can put the function into the Taylor series. Okay, maybe sine x or cosine x, you can put them here. Okay, so the point, or what you will do is, you have a function, you derive the function maybe 3 or 4 times, check the coefficient, put back into the series, and that's becoming your Taylor series. Okay, it's practically repetitive. It will be disaster if you are wrongly doing the derivatives part, because it will be all wrong. So you need to be careful here. Okay. And then what is the Mclaren series? So the Mclaren is actually, if you have, so if let's say if a is equal 0, then the functions will be equal and because a is 0, then I can write just x. For this part, is just x, and then plus, and this is actually what we call, or let me, this series is called the Mclaren series. And because you see, between Taylor and Maclaurin, the one that has more reasonable approach is actually the Maclaurin. So frequently, the Mclaren will be appearing in some, I think, most of the problems. Okay? But it's actually part of the Taylor series. So Mclaren is just the same as Taylor series, but the A is 0. So you just need to put A equals 0 and then change the formula into this formula. Okay? What you are seeing is, you see, it's just F 0, F, and then F prime, and then 1 factorial, f double prime 0, 2 factorial, x squared, this is x, this is the third derivative, 3 factorial, x cubed. So it has the pattern. So you can continue the pattern if you want, f with the fourth derivative, and then x with the power of 4, divided by 4 factorial, and so on and so forth. Okay. Okay, that's the Mclaren series. So let me give you some illustration or any questions so far. Okay. I think the best way, if you want to see how it's connected, is um, you can go back to here, the first one. So the first one, we start by our general terms. We derive that, and we check if x equal a to find its coefficients. Okay, and from here we can relate the coefficients with the pattern of a functions with some n here, meaning we can see this as, we can derive these functions into several, or maybe into some n terms, and defined by n factorial, and it's become a pattern in the series, okay, in the Taylor series. Okay, so that's how we get this the series here. Okay. Okay, now now let's see the functions of 1 divided by 1 minus x. Okay. Okay. If we are looking this at Maclaurin series, if this is Maclaurin series, then the Cn should be given by f n, and then the value will be 0, and then n factor. Okay, to confirm this, we can check. So if we remember what the 1 over 1 minus x is actually our geometric sum, or we can write its sum as x with the power of n. Or if you want to expand this, we can expand this, become 1 plus x squared plus x cubed plus dot dot dot. Okay? And we can conclude that the ratio should be less than 1 to be convergent. Right? Now, if you want to observe whether the functions in the Maclaurin series, okay, is true or not, then we let's just write the functions here. And the first thing you need to do is you need to derive several times. Okay? You need to derive several times. So f prime, the first derivative is 1 divided by 1 minus x squared, right? And we derive one more time, and it will be 1, 2, right? We multiply by 2, the chain rule from the functions. And this become cube. And f right? 3 is from the functions before. So you get 1 minus x and 4. Okay, and then check the value at x equals 0. So this will be 1, and this will be also 1, and this will be 2. Or let me write as, wait, 1, 2. And the third is 1, 2, and 3. In general, let me write in terms of Fn. So you have f and x is equal n factorial. If you see the pattern that we comes up, okay, 1, 2, 1, 2, 3, and then if you derive another functions here, 1, 2, 3, 4, 1, 2, 3, 4, 5, okay, we can say it's n factorial. N factorial divided by 1 minus x and then n plus 1. Okay. And if you are substitute the 0 into the functions, it will be equal to n factorial. Okay. And then the coefficient will be equal and you can see that this n factorial divided by n factorial, it's equal 1. Okay. So Cn is 1. That's why this 1 minus x, we can write this as so only x with the power of n, okay, because Cn is 1. So we don't really need to write C here, right? This is just to proving that this is exactly 1, okay? Okay. Because the formula, the basis formula is Cn and x minus a, right? And because we are seeing here, it's only x, so probably the a is 0, and maybe it's Mclaren series. And we try to see the Mclaren series and try to prove that, okay, what is the Cn from this Mclaren series? It's actually just 1. So the coefficient is true that this is 1. So we can see 1 over 1 minus x is, we can develop the Mclaren series. And we can prove that, okay, it's true that this is correct. Okay, so we can also see these functions as a Mclaren series, and we prove that it's actually true that it's x with the power of n, this series. Okay, aside from what we have done before, we have done the geometric series, right? So we can see this. Okay, this is geometric series, and this is also we can see as a Mclaren. Okay, because there is no a, so probably a is 0, and we try to prove that, and it's actually true that it's the coefficient is just 1. Okay. Let me write the suppose equations. Okay. Suppose equation is this. So because this is the general terms, we have this term, and maybe a is 0, so it's x with n, right? But we still confused about Cn. How is true for this x with the power of n? To find the Cn, we can try the Maclaurin series because we see the a is 0. Okay, that's how it's done. Okay. Okay. So first, you can see the functions, and maybe you can check the sum of the derivative. Maybe 3. I'm suggesting at least 3 derivatives you need to try. See the forms, okay? And then if it is just proving maybe some functions here, and maybe you think maybe a is 0, then you can try the Maclaurin series and see what the expansion of the series will be. And you can see the coefficient, you can see the expansion, how it would be, and you can make some conclusion from there. Okay. Okay. Now let's give you another example for the Mclaren series. Yeah, practically one question you need to pay attention to derivative, and you may need some um, long solutions usually. Okay. But that long solution is basically you need to derive 1, 1, 1. Okay. Okay, that's the Taylor and Maclaurin series. Let me give you another view for how or what is the applications. Okay. But let me give you the example here. Let's say the functions is exponent. Okay. And find a Mclaren series and R, the radius of convergence. Okay. Radius of convergence. Okay. So first, let's see the form of for the functions itself. Okay. I think I've been giving some parts of introductions of e to the x in the last semester, because if you try to differentiate e to the x, it will be the function itself, right? So let me write the f n and x. It will be always e to the x, right? It will be with power of x. And when x equals 0, then it's just 1, right? For all n. So therefore, okay, this will be sum from n equals 0, x to the n divided by n factorial. And that is 1 plus x 1 factorial plus x squared 2 factorial plus x cubed 3 factorials plus. So we can write the e to the x is actually 1 plus x Okay, that's the e to the x. I think I have given you this form last semester, but just to overview what is e to the x. And then remember to find the ratio or to find the radius of convergence, you need to find the ratio. So we need to use the ratio test. And let the an is equal x with the power of n and n factorial. So we try to put that sequence okay. Now we have the x, and so we have absolute value of x divided by n plus 1. And let me write here. Don't forget to write the limit as n approaching infinity. And it will be approaching 0. Okay, and this is already less than 1. So what is happening now? Radius of convergence is, or r is equal. What is happening if the result is 0? The r? Yes? Oh, yes, yes, true. So r will be infinite. So we can say that this the series converge for all x or always converge. Yeah. Okay, this is from the power series. You can check. We have three possibilities. The R can be some interval. It can be only in one point or in every x. Okay. Okay. So how we can make this in our mind? Okay. So look at this limit of n. Okay. So if you want, you can write this in terms of um, limit n, and the other part is x. Okay. The left part is n, the right part is x. Two different variables that you cannot mix up. Okay. So first, this terms on the left is it's already 0, right? So whenever you find any x, it's always been 0. That's why it's all x, always converges. Okay, get it? So that's how you see the point of view for the limit. Okay, okay, that's the power series actually. Okay, so that's the e to the x. Okay, let's give you some questions that really important. When is a function represented by its Taylor series? So let's say we are determining the e to the x, and we know that this is the sum is, you can write like this, the series. So how can we, or let's say, does e to the x have power series representations? So what the question means is, from what we've done before, the previous one, we have functions e to the x, and we are trying to find the Mclaren series, and we find the radius of convergence. But the question really is, uh, how can we determine the e to the x? It does have the power series. Okay. So you can change this e to the x to any random functions, but the question is still relevant. How you can determine any functions having its power series representations. Okay. Now, this need to be uh, observed by, I think it's much more easier in graph. But before graphs, let me try to write down some. So let's say the fx. Let me write the general formula. So in Taylor, we know that this is the formula, n factorial and x minus a with power of n. This is true when f has derivatives of all order. So you can derive many times. Okay, and then in the if we are looking at the convergence series, so fx or the functions is the limit of the sequence of partial sum. Okay. Let me write t and x as the partial sums. Okay. To differentiate, maybe it's I until some n. Okay. And then I factorial, and then x minus a I to the power of I. So the partial sum, we can think maybe the first one, and then the second one, the third one, and until some n. Okay. Let me move this first. Okay. Let me write this as from FA and then plus okay. So this T and X. Okay. So what does T means? T in these terms is the partial sum. So if you have T1, it's only this part until this. Okay. If you have T2X, it's this until this. If you have T3 until 3, if you have N, you have plus until N. Okay. Okay. If you see the terms, okay, this is a linear. Okay, the first one is linear, right? The second one is the squared or parabola, right? The cubic. So uh, we can observe that from here, the Tn is polynomial or and degree polynomial. Okay. So if we check each one, from 1 is just 1 plus x, and from 2, from n equal to, it will be 1 plus x squared divided by 2. And if you have order of 3, you have 1 plus x squared over 2 plus x cubed over 3. Factorial, sorry. And you can add 4 or 5 if you want. But from here, if you can think any graphs, okay, it's to see it clearly, you will see that this is a linear graph. This is a parabola. This is a cubic, right? Now, let me draw the graphs for you here, maybe here. Let me draw the e to the x first. Okay, maybe that. Let me write this, or maybe y. Y is e to the x. And this is 0, 1, this point. And then maybe here, okay, maybe this is y equal t1x. And then the other one, maybe like that. And this will be y equal maybe t2x. Okay. Maybe it's more like that. Okay. Now the last one. The last one is quite difficult to draw. Oh wait. Okay. Okay, the green one, the last one will be the t3x. Okay, hopefully you can see what I'm trying to do here. If you see from t1x, okay, and t2x, so the light blue, and then go to the dark blue, and go to the green one. It's increasing 1, 2, 3. The order is increasing. Okay? So the partial sums, if you increase n, it will be approaching the e to the x. If you have free time, actually you can try in the graphing calculator or some websites. Try just to put in the equations, and you will see the graphs will approaching this e to the x. Okay. So what we can conclude from here is actually the functions is the limit of this partial sum. Okay. So when we increase the order of n, we can actually approaching the function itself. Okay. So we can actually using the limit relations, okay, to see from the graphs. And we can say also if we let the Rn so the fx is Tn x plus Rn x. Okay, so we are moving to another thing from here because we are doing limit. Like I said before, limit is our approach, getting closer, closer, closer. But it's actually not the same. Okay, f and Tn is not the same. But in limit, maybe it's close. It's closer, closer. So we will have some R that we call remainder, or in sense to make it easy to understand, sense of error. You will have some error, like the gaps between the real functions and the approximation, right? Okay. So we can also see this as an error, or let me write Rn is called the remainder of Taylor series. So if limit of n of this Rn is equal 0, then and it's actually or it's just fx. Okay, so if the limit of the remainder we can prove it to be 0, then the limit of the partial sum will be equal to the f of x. Okay, and this is just a reverse of what we did on the left. Okay, but in terms of the remainder. Okay, yeah, this is the proof of the left one. Okay. So in some cases, if you want to know whether your functions or your formula is close enough, or you want to know how much error you want to, or how can you maybe minimize the error and so forth, this is how you are going to observe. Okay, you need the remainder, or let me write in the terms in more official way. Let me move to okay. Let me move to the next slide. Okay. So if functions is Tnx plus Rnx, where Tn is n degree Taylor polynomial of functions at some value, say, let's say a, and if limit so for x minus a less than r, then f is equal to the sum of its Taylor series on interval x minus a less than r. So to determine how you are going to use the series, first you need to CVP. Okay, you need to see that that is the polynomial. Okay, so you need to try find some derivatives and put in the Taylor series equations, and you need to make sure that okay, that's the polynomial, and thus you can use the Mclaren series or Taylor series. So meaning the functions need to be you can derive the functions as many times as you want. That's the key for this series. Okay. Okay. Aside from this, we can also write in terms of we call the Taylor's inequality. So if let's say we have this absolute value of functions less some value of m for the interval less than d, okay, then the Rn satisfies okay. So uh, it's actually will be um, we will observe these terms or this inequality actually in the 1111, the application of Taylor polynomials. But I think I will skip it for now because it's uh, the concept is it's like iterations. So you will approximate some functions with some of numbers. But actually, the concept, the core of the concept, will be based on what we have done in the Maclaurin and Taylor series. So I will maybe skip it, the 1111. Okay. Okay. We still have time. Let me go to some how to use uh, the Taylor or the Maclaurin. So let me write the proof. E to the x is equal to the sum of its Mclaren series. We have done the e to the x is x with the power of n divided by n factorial. But let's see from here. So the functions e to the x, and let's write the n plus 1 x. It's still e to the x, okay, for all n. So if the x is less than d, because a is 0, this is Maclaurin, and d is positive number, then the f is e to the x less or equal e to the d. So with a equals 0 and m equal e to d, okay, so let me write some notes here. Notes, m equal e to the d, it's works for every n, and we have from the limit, the tn before, we have ed n plus 1 factorial, and then x and n plus 1. E to the d is a constant, and this will be what we approach here. It's equal 0, and then limit of n approach infinity of Rn is equal 0, uh, by the squeeze theorem. If you look at the Taylor's inequality, okay. So what we have done is we are looking for any m that might uh, that we can utilize and put here. So we need to prove that if this limit is 0, and we can prove the Rn is also 0 for all value of x. Because from here, this n is 0. So all x will be, it can be, or it works for every x. Okay. So for all value of x, and then we can write that the e to the x is equal to sum of its Mclaren series. Same conclusions, but uh, different perspective or different angle of view. So this is if we want to look at the Taylor's inequality, which means we need to consider the remainder that might comes up. Okay. But since the uh, since the e to the x is works as e to the x for every form of derivatives, and if we have this assumptions that x is always equal some positive number, then our functions in absolute value here will be always less than this e to the d. Okay, so we can put this e to the d as our m. Okay, we can put this e to the d as our m. So this part here is our assumption. Okay, is our assumption. So d, we need to find some d in some value. Okay. So sometimes if it is using a number, sometimes you need to maybe you need to think what number you need to apply to this d to works your functions, okay? So that the function is works. So if we put d there and we have this m for every n, then we can approach this and we see the limit. Okay, we see the limit, and it's true that the limit will be 0. And by the squeeze theorem from this, okay, this is less than this and less than the uh, less than this. So the parts will be equal to 0. So the remainder is 0 for all value of x. Okay, and it's again proving that the e to the x is the sum of x to the n divided by n factorial. Okay, this part is just proving how Taylor's inequality works. Okay, but in reality, the applications might use some iterations. So it might use some numbers, and you might deal with some real percentage of error. How many percent that the sum will be how accurate the sum to the functions. Okay, so you have maybe the functions, and you need to approach the function with some series. So how close the series will be, that will be your R. Okay, that's the real application. Okay. This limit is just a concept to help you actually simplify the problem. Okay. If not, then you're because we are um, at least in the curriculum of engineering, you will engineer that thing. Okay, maybe you want to calculate maybe a pipeline. You need to calculate how this the flow rate of the water flow, and you might need some physics, fluid dynamics, but most importantly, you need how to visualize some graphs to help you see better, because sometimes graph visualizations is more powerful than just a number. Okay. I think I will stop here right now. We still have some parts for another exercise to find other functions. Maybe I can give some lists for you. We have done this. We have done this. You can try at home from sine, cosine, and then tangent inverse, and then ln. And the textbook is actually having binomial, but I think I will skip the binomial for you. Yeah, you can try this, and this. You try to find mm, I think just find the Mclaren series. So from the sine, cosine, tangent, ln. So the steps is the same as I mentioned. Find the first derivative, second, third, maybe fourth, and then equaling a to 0, and put back the equation, the expansion, and find the formula for the sum. That's it for the Maclaurin series. Okay. I think I will stop here, and hopefully you can have more exercise with your TA this Friday.